So we talked about expansional cooling and adiabatic processes and the parcel. And we talked about the fact that all condensation is the result of expansional cooling, but not all expansional cooling produces condensation. Now we're going to talk about expansional cooling as an adiabatic process for a parcel that does produce condensation. Okay, because you already know that condensed air is not dry, it's saturated, and condensed air releases latent heat. It can rise, and as it rises, it can still cool by expansion. And we've talked about that because we know that the top of fog radiates and emits its warmth and cools so that it condenses more. But in the meantime, the latent heat of condensation is in the center of the cloud, and that latent heat of condensation forces the cloud to rise a bit more. A lot going on inside a cloud. And when we need to put this into mathematical form and graphing form, we know that after the cloud has formed, after the parcel has condensed, we can't still talk about the dry adiabatic lapse rate because the parcel is no longer dry. It's now condensed. So that's what we're going to discuss on this video. To go back a second, in the big world of parcels, like I had mentioned to you, you start at the surface with a dry parcel. And you lift with the dry adiabatic lapse rate until you hit the level of condensation. Now, what is the level of condensation? Well, it is very, very important, real world. Literally, the level of condensation will be the critical issue in the NTSB investigation of the Kobe Bryant crash. It's that important. Literally, it kills people. So finding the level of condensation, or as it's known, the LCL, the lifted condensation level, you are finding the lowest altitude where fog base forms, or the lowest altitude where a cloud forms. Let's see how you do that, because you already know a lot of this. You already know that a cloud forms and condensation forms when the temperature of the parcel goes down to the temperature of the dew point. So the temperature of the parcel in rising drops its temperature and meets the dew point. You already know that. And now we're going to learn what you probably already are thinking about finding that level of condensation on a sounding. And then in homework, you're going to do it on a table. And then you're going to convert it to a graph. So you're going to make your own sounding. You've already made your own sounding before with altitude and Key West and Anchorage, I think, right? So you can add in this as well. Let's start easy. Let's start with finding the level of condensation on a sounding. What you know on a sounding, just to review, is that the red is the environmental lapse rate, and the dew point is the black dashed line. Now we're going to get to the point where you understand that the parcel temperature lapse rate is in yellow. Here's your parcel temperature lapse rate. Let's go over how we get that in there. The balloon goes off at the surface and it starts taking measurements. It starts taking temperature measurements right away. At the same time, it takes a parcel measurement right at the surface. And that's the last thing the balloon records for the parcel, the imaginary parcel. Everything we do to construct the parcel in yellow here, we do by calculations. They're very simple calculations. Literally, they're addition and subtraction. So the sounding balloon takes the measurements for the red line and takes the measurements for the black dotted line. We create the measurements for the yellow line, the parcel lapse rate. Where the parcel lapse rate, as we've calculated it, meets the dew point lapse rate is where the level of condensation is. So right here's where they meet. You move over and you report it as either an altitude or as a pressure. You can see it done both ways. This one's right at about 800 millibars at about 2,076 meters. That's the level of condensation on a sounding, where they intersect. Now, you can also find this in a table, and you can also construct this from a graph. You're going to do that for your short assignment. We'll get into that later. From the level of condensation, the cloud, the condensed parcel, may continue lifting. It may continue lifting from a topographical lift, from a convergent lift, or for a frontal lift, or from a frontal lift. We're going to go over the frontal lifts in Chapter 8. If it does not get lifted, it's probably going to stay spread out as a fog. That's why fogs are so flat. They are not lifted continuously by these other forms of lifting. After it is condensed, it no longer follows the dry adiabatic lapse rate. Instead, it follows what's called the moist adiabatic lapse rate. It is different. It is 6 degrees Celsius per 1,000 meters, as compared to about 10 degrees Celsius per 1,000 meters. This is a lapse rate that loses warmth more slowly than the dry adiabatic lapse rate. The cloud can become warmer than the environment because the cloud loses warmth more slowly. That means that the cloud could be more buoyant in the environment and continue climbing and rising and cooling and condensing and rising and climbing and cooling and condensing until it meets the stratosphere. And the stratosphere, as we know, is warmer than the troposphere. Suddenly that cloud is not going to be more buoyant than the cooler air in the troposphere. That cloud is going to have a lid on top of it. That's where you see the anvil for a lot of thunderstorm clouds. The moist adiabatic lapse rate is 6 degrees Celsius per 1,000 meters. You can think of this as your mnemonic for steep lapse rates. You can think of it as your mnemonic for a stingy loss in temperature per 1,000 meters. It's actually less than your dry adiabatic lapse rate, so it's a little stingier, it's a little steeper. It's kind of like wet soil loses heat more slowly than dry soil. Same concept here. If you are cooling off wet soil, it's going to take you longer to do that. If you're cooling off a cloud in higher and higher atmospheres, it's going to take you longer to do that. It has a steep lapse. Let's go back and look at that if you need to. 6 degrees Celsius per 1,000 meters. Why? Why is the moist adiabatic lapse rate lower than the dry adiabatic lapse rate? Because you are releasing latent heat when you condense, and you are continuously condensing as you're moving up and climbing. And as a result of releasing that latent energy, you're slowing the heat loss to altitude. Okay? Heat loss to altitude is always going to be there. You're just going to slow it less when you have that latent heat released. So, to sum up, this parcel that you start with at the surface, it begins its climb with a dry adiabatic lapse rate of 10 degrees per 1,000 meters until you get to the level of condensation that you found on the sounding. And after that, the parcel, the yellow line, continues up at 6 degrees Celsius per 1,000 meter lapse rate. Very important to remember. I'll see you on the other side to go over it more.